So as part of the bell ringer, we're just looking at where the vertexes are. So the vertex of the first graph is 0, 0. That is the absolute value parent function, meaning that is the graph that is not transformed. It is right where it would be if we just looked at the absolute value of x. As our graphs are transformed, we can reflect them. So a negative in front of the absolute value reflects it across the x-axis. The positive 3 after shifts the graph up 3 units. So this is an absolute value graph shifted up 3 and reflected. The reason we start talking about the words reflection and shifting is because all of those same properties with reflecting, shifting, left, right, up, and down with absolute values directly corresponds to quadratics. So the formulas are very similar and the transformations are very similar. The vertex of the quadratic is very similar to the vertex of the absolute value. It will be where the max or the min occurs. So this has a min, max, min. So like I said, today is a lot of vocab. We're starting on a new chapter. Our new chapter focuses on quadratics. So in this chapter, you're going to hear me use the word parabola. A parabola is simply the name for the shape of a quadratics graph. So if you have a linear function, its shape of its graph is a line. If you have a quadratic, the shape of its graph is a parabola. A parabola is the graph of a quadratic. It is a U-type shape. The quadratic function can be written in two forms, standard form or vertex form. Standard form is ax squared plus bx plus c. Vertex form is much like the vertex form of an absolute value. In this form, you see the vertex of the graph. So in vertex form, you can see the vertex of the parabola. We have our line of symmetry that divides the parabola into two mirror images. So quadratics are symmetric, just like absolute values. So if you graph one side of the quadratic, it's mirrored on the other side. The mirror occurs at the vertex. The vertex is the min or the max of the parabola. Its equation is h comma k. So we're going to use that graphing space to graph the parent function. The parent function of the absolute value graph and the quadratic are similar in that the vertex is at 0, 0. What is different is the table. An absolute value graph is linear, meaning the slopes of the line are 1 to 1. A quadratic is not the same. The table for the quadratic function is our perfect squares. So if the x's are 0, 1, 2, it's the perfect squares that match them. So that's 0, 1, 4. If this continued, 3 becomes 9. 4 would be 16, so on and so forth. So the quadratic graph goes based off the perfect squares. So it's 1, 1, 2, 4, 3, 9. And then because it's symmetric, it would be 1, negative 1, 1, negative 2, 4, negative 3, 9. Today we're going to focus on really graphing our quadratics from that parent function and understanding how the a value affects the graph. So the A value will affect how narrow or compressed the graph is. So if an A value is greater than 1, it'll be stretched. If it's smaller than 1, it will be compressed. So that's what those two images depict down at the bottom of that page, the stretching versus compressing. How are we going to graph these? So we're going to focus on plotting our vertex and then plotting the points to the right and to the left of the vertex using the idea of the perfect squares. Okay? So if you have a function such as 1/2 x squared, the parent function would be at 0, 0. The vertex of the compressed or stretched graph will stay the same. This graph isn't shifted left or right, so its vertex is also at 0, 0. The only value that we're affecting right now is the A, and my A is equal to 1/2. So that means that this graph is compressed. Being that it is compressed, that means that the graph is going to be wider than the parent function. So it's less steep. So what happens is that if the values of x are unchanged, they're going to stay 1, 2, and 3. What's going to be affected is my y values, and they're affected by a ratio of 1/2. So the original points are 0, 1, 2, 3, 0, 1, 4, 9. So to plot your new points, we're just going to take those original points and multiply each of them by 1/2, because that's what it's being compressed by. So it's like 0 times 1/2, 1 times 1/2, 4 times 1/2, 9 times 1/2. This table could technically continue. It'd be like 4 and 16 times 1/2, and so forth. So your points would be 0, 0, 1, and then 1 times 1/2 is 1/2. So it'd be like 1, I'm going to use the mouse, and then 1/2. And remember, if it goes to the right, it also does the same symmetrically to the left. 2, instead of being at 4, is now at 2. So you have the point 2, 2, and -2, 2, because it's compressed by that 1/2. 3, instead of being at 9, is now at 4.5. And then 4, instead of being at 16, would be at 8. So there's your quadratic function that is wider than the parent. So if the A value affects the stretching and compressing, the A value also affects the direction the graph opens. So if a graph is reflected, it opens down like a frown. So what do we predict will happen to the graph of f of x equals ax squared if a is negative? So what that means is this looks like y equals negative ax squared. And what that means is that the graph will reflect across the x-axis. Or like I said, open down like a frown. So a negative a forces the graph to open down. So we have reflection. Reflection also directly relates kind of to concavity. So you might hear me say a graph is concave up or concave down. Concave up is kind of like the smile. It's where the graph is opening up. Concave down is where the graph looks like the frown and is opened down. So we talk a lot about concavity with polynomial functions because one polynomial can be both concave up and concave down. So like a cubic will be both concave up and concave down because it has a point of inflection. And that's what we're going to get into when we get to chapter 6. And those of you that take physics or get to trig or AP Calc, they focus a lot on concavity. The effect of the A value in quadratics is very similar to the effect of the A value with absolute values. The negative reflected it. An A value between 0 and 1 compresses it. An A value greater than 1 stretches it. So all those rules are the same. So what we're going to do is continue to practice graphing these types of functions using those rules. So we're going to continue to graph these types of functions using those rules and the idea of that table. So the parent function is always 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. What you're going to do is apply the stretching or compressing to the y value to find your new points. So in that table, kind of for your homework, the x value will always be the same for right now. What you're going to do is take the y value and multiply them by a. So the parent y values are 0, 1, 4, 9. So to get those new points, because there's not a slope like there was with absolute values. And the reason I have you using that table and doing it this way is that once we start shifting the graphs left, right, or up and down, you're going to see how they directly relate to the table. So I know for today some of you might not need that table, but it's just that the table is going to help us tomorrow. All right, so your homework's the front of that next page. I don't know if there's a back. I can't remember. I made them before break. No, yeah, you just have 20. What? Say 5 times 4. Ow.